This is the EdExcel A-Level Further Maths Paper 1 from the 2021 series, and this paper covers the core pure content. Question number 1. The transformation P is an enlargement sent to the origin with scale factor k where k is greater than 0. The transformation Q is a rotation through angle theta degrees anticlockwise about the origin. The transformation P followed by the transformation Q is represented by the matrix M, which is equal to minus 4 root 3, 4 root 3, and minus 4. For part A, we have to determine the value of K and the smallest value of theta. Well, if we have a transformation, which is a rotation through angle theta degrees anticlockwise about the origin, that would mean we would at some point have to use this matrix over here. Now, M is equal to P followed by Q, and so we would have to work backwards. So for part A, we have M, which is equal to Q multiplied by P. We have P followed by Q, so we work in this order here. The matrix Q, that's this here, we have Q equaling cos theta minus sine theta, and cos theta. The matrix P, if we enlarge by scale factor k with the center at the origin, that matrix will be k, 0, 0, k. And the result of all this is equal to M, and we know what M is. That's minus 4 root 3 minus 4 root 3 and minus 4. We can determine the value of k and theta. We would begin by multiplying these matrices together. Cos theta times by k plus minus sine theta times by 0 is k cos theta, and then we have cos theta times by 0 plus minus sine theta times by k, so that would be minus k sine theta, and then we have sine theta times by k plus cos theta times 0, so we've got k sine theta, and then we've got sine theta times by 0 plus cos theta times by k. That would be k cos theta. The result of this matrix, we have minus 4 root 3, minus 4 root 3, and minus 4. We can now determine the value of k by comparing elements. We have k cos theta, which is equal to minus 4, and we have minus k sine theta, which is equal to minus 4 root 3. And we can solve these two equations simultaneously. If we divide the equations by each other, first of all here, the minuses cancel from both sides. So if we do this equation divided by this equation, we have k sine theta, which is equal to 4 root 3. And then we will divide this by k cos theta, which is equal to minus 4. And so what you can see here is tan theta is equal to minus root 3, from which we can conclude theta is equal to 120 degrees. And knowing that theta is equal to 120 degrees, we can now find out the value of k. So we have k times by the cosine of 120. This is equal to minus 4. So if we solve, cos of 120 is minus a half, so we have minus 4 divided by minus a half, which is 8. So we can conclude k is equal to 8. Now for part B, a square S has vertices at the points with coordinates 0, 0, a minus a, 2a0 and aa, where a is a constant. The square S is transformed to the square S dash by the transformation represented by m. For part B, we have to determine, in terms of a, the area of S dash. Well, here we've got the diagram of S. Now, what we can do is find out the area of this. And what you'd hopefully find is we have two triangles. And so if we were the area of S, the area of S is equal to 2 lots of, well, here we've got a triangle, 1/2 times by the base, which is A, rather the base, which is 2A, and the height, which is A. So if we work this out, we get 2a squared. This is the area of S. And so, therefore, the area of S dash is equal to 2a squared, and then we will multiply this by 8 squared. The reason we multiply by 8 squared is because the 8 squared here represents the area scale factor. K is the length scale factor, so k squared is the area scale factor. And knowing that k is 8 squared would then be the area scale factor. 64 times by 2 is 128, times by a squared it turns out the area of S dash is equal to 128 A squared. Question number 2. For part A, we have to use the Maclaurin series expansion for cos x to determine the series expansion of cos squared of x over 3 in ascending powers of x up to and including the term in x to the 4. We have to give each term in simplest form. So we would begin part A with cos squared of x upon 3. And what this is the same as is cos of x upon 3 squared. Now, if we go to the formula book, under the section involving Maclaurin's and Taylor's series, we have a series expansion given over here for cos x. Now, in the question, we don't have an x, we've got an x over 3. So we will replace the x with x over 3. And so if we work this out, let's begin by opening big brackets over here. We have 1 minus, well, instead of us having x squared over 2 factorial, we have instead x over 3 squared over 2 factorial, and then we add on x over 3 to the power of 4 over 4 factorial, and then we could continue. Now this result here is being squared, so we're going to multiply this by itself. So if we work this out, we have 1 minus, now here we've got 1/9 divided by 2, so that's 1/18, so we subtract x squared over 18, and then we have 1 over 3 to the power of 4, and then we will divide this result by 4 factorial, which is 1 over 1944. So we add on x to the power of 4 over 1944. And then we've got other terms. Now, this is being squared, which means we would have to multiply this by itself. And that's what we see here. Now we want to expand up to and including the term involving x to the 4. We have 1 times by 1, which is 1, and then we've got 1 times by minus x squared over 18, which is minus x squared over 18, and then we've got 1 times by x to the 4 over 1944, so we add on x to the 4 over 1944, and then we've got minus x squared over 18 times by 1, so that's minus x squared over 18, and then we've got minus x squared over 18 times by minus x squared over 18, well, that will be positive, and then we have x to the 4 divided by, well, 18 squared is 324, so we add on x to the 4 over 324. Now if I do x squared times by x to the 4, I get an x to the 6. So I'm not interested in that term. And if I do x to the 4 over 1944 times by 1, well, we add on then x to the 4 over 1944. And then we've got other terms which we can consider, but we want to stop off at x to the 4. And if we tidy this up, we've got 1 minus x squared over 18 minus another x squared over 18. That's minus x squared over 9. And then we've got 1 over 1944. We add on 1 over 324. And then we add on another this. So we've got two lots of this. So we add on x to the 4 over 243. So we have worked out the series expansion up to and including the x to the 4 term. Now for part B, we have to use our answer to part A and calculus to find an approximation to 5 decimal places for the integral of 1 over x lots of cos squared of x over 3 with respect to x in between pi over 6 and pi over 2. So for part B of the question, we've got the integral from pi over 6 to pi over 2 of 1 over x times by cos squared of x over 3 dx. So if we work this out, what we can do is use our series expansion. Cos squared of x over 3, that's what we worked out here. And so we have 1 over x multiplied by 1 minus x squared over 9 plus x to the 4 over 243. So if we attempt to simplify all of this even further, we have the integral from pi over 6 to pi over 2, and if I multiply the 1 over x into this bracket, 1 times 1 over x is 1 over x. 1 over x times minus x squared over 9, that's minus x over 9. And then we've got 1 over x times by x to the 4 over 243, that's positive x to the 3 over 243. And we're integrating with respect to x. So if we integrate this, well, integrating 1 over x, we end up with the natural log of the mod of x. And then integrating minus x over 9, we end up with minus x squared over 18. And integrating x cubed over 243, we end up with x to the 4 over 972. So what we need to do now is evaluate this in between pi over 6 and pi over 2. So, for the upper limit, we've got the natural log of the mod of pi over 2 minus pi over 2 squared over 18, and then we add on pi over 2 to the power of 4 over 972, and then we subtract our lower limit, natural log of pi over 6 minus pi over 6 squared over 18 plus pi over 6 to the power of 4 over 972. So if we work this out, well, let's substitute in pi over 2 for our upper limit, store this into A, and pi over 6 will store into B for our lower limit. So for the upper limit, we've got the natural log of pi over 2 minus pi over 2 squared over 18 plus pi over 2 to the power of 4 over 972. And for our lower limit, we've got the natural log of pi over 6 minus pi over 6 to the power of 2 over 18 plus pi over 6 to the power of 4 over 972. So if we work this out, we get 0.9829514,389. So to 5 decimal places, we get 0.98295. Now for part C, we have to use the integral function on our calculator to evaluate this integral, give your answer to 5 decimal places. So the calculator value of this result here, if we substitute this all into our calculator, use the integral function, we have 1 over x, lots of cos of x over 3, and then this is squared, and then we evaluate this in between pi over 6 and pi over 2. So let's just make sure we are in radians. It turns out we get 0.982,801,2317, which, if we go back to the question to 5 decimal places, we've got 0.98280. And now for part D, assuming that the calculator answer in part C is accurate to 5 decimal places, we have to comment on the accuracy of the approximation found in part B. Well, if we compare this value with this value, you can see our answer to part D, B and C, those values are the same given to 3 decimal places. So if we take a look at 3 decimal places, we get 0.983 to 3 decimal places. So the approximation is correct to 3 decimal places. And of course, to 3 decimal places, we have 0.983. Question number 3. The cubic equation ax cubed plus bx squared minus 19x minus b equals 0, where a and b are constants, has roots alpha, beta and gamma. The cubic equation w cubed minus 9w squared minus 97w plus c equals 0, where c is a constant, has roots 4 alpha minus 1, 4 beta minus 1 and 4 gamma minus 1. Without solving either cubic equation, we have to determine the value of a, the value of b and the value of c. You will find that each of these roots are in the form 4 times by something minus 1. So what we will do then, we begin by letting w equal 4x minus 1. Each of these roots are of this form here. And so if we rearrange for x is equal to w plus 1 over 4. And knowing that x is equal to w plus 1 over 4, we can substitute this back into here. And so if we do that, we have a times by x cubed, so that's w plus 1 over 4 cubed, plus b x squared, so we've got b lots of w plus 1 over 4 squared, minus 19x, so that's minus 19 lots of w plus 1 over 4, and then we have minus b. This is equal to 0. So now we can simplify all this. Well, we have over here a over 4 cubed, which is 64, and then we will multiply this by w plus 1 all cubed, which is w cubed, plus 3w squared, plus 3w plus 1. And then we add on b times by 1 over 4 squared, so that's b squared, rather that's b over 16. Of course, 4 squared is 16. And then w plus 1 all squared is w squared plus 2w plus 1. And then we subtract 19 over 4, lots of w plus 1. We then subtract b. The result of this is 0. So let's multiply the terms on the outside of the bracket into the bracket and simplify as much as we can. So if we do that, we have a over 64 w cubed, and then we add on 3a over 64 w squared, and then we add on 3a over 64 W, and then we add on A over 64, and then we add on B over 16W. We then add on 2B over 16W. We then add on B over 16. We then subtract 19 over 4W, subtract another 19 over 4, and then we subtract B. The result of all this is equal to 0. Now let's gather all like terms together. We have, for the W cubes, A over 64 of them. And in terms of the W squareds, well, we have 3A over 64. And then we also have B over 16 of them. In terms of the W's, we have 3A over 64. And then we have 2B over 16. And then we have minus 19 over 4. And in terms of the constants, we have A over 64. And then we have B over 16. And then we have minus 19 over 4. And then we have minus B. And all of this is equal to 0. Now, because 16 and 4 are factors of 64, we can write everything over a common denominator of 64. We have A over 64W cubed, and then if we have the denominator here as 64, we need to multiply this B by 4. So we add on 3A plus 4B over 64. So this is the W squared terms. And then we have 3A. Now we need to multiply 2B by 4 to get 8B. And then we have 16 times by minus 19, so that's minus 304. And then we divide this by 64. So this is the term involving W's. And then the terms involving the constant terms. We have A, and then here 4B, minus 304, minus 64B, all over 64. This is all equal to 0. Now, if we tidy all of this up even further, we have a over 64 w cubed plus 3a plus 4b over 64 w squared, and then we add on 3a plus 8b minus 304 over 64 w, and then here 4b minus 64b, that's minus 60b, so we add on a minus 60b minus 304 over 64, and this is all equal to 0. Now, if we compare with this equation here, well, we've got a 1 w cubed, so we need to multiply through by 64 and then divide through by a. And if we do that, we have w cubed plus 3a plus 4b over a w squared, and then we add on 3a plus 8b minus 304 over a w, and then we add on a minus 60 b minus 304 over a, and this is all equal to 0. If we now compare coefficients, well, in terms of the w squareds, we have minus 9 of them, and in terms of what we have here, we've got 3a plus 4b over a of them. So comparing the w squareds, you can see we have 3a plus 4b over a, which is equal to minus 9. Multiplying through by a, we have 3a plus 4b equals minus 9a, from which you can see 12a plus 4b is equal to 0. Now, if we compare the w's, you can see we've got minus 97 of them, and here we have 3a plus 8b minus 304 over a of them. So if we compare the w's, we have 3a plus 8b minus 304 over a. This is equal to minus 97. So if I multiply through by a, we have 3a plus 8b minus 304 equals minus 97a, from which we can conclude 100a plus 8b equals 304. And now if we compare the number terms, you can see we have C of them, And here we have a minus 60b minus 304 over 8 of them. So if we compare the number terms, we have a minus 60b minus 304 over a. This is equal to c. If I multiply, well, we'll leave this alone for a sec. If I call this equation 1, and this equation 2, and this equation 3, we can find a and b using equation 1 and equation 2 and sub those values into equation 3 to find the value of c. So, if we find the value of a and find the value of b, we have 12a plus 4b equals 0, 100a plus 8b equals 304. A is equal to 4. B is equal to minus 12. We know the values of A and B, so we can sub these into equation 3. So we have C equals A, which is 4, minus 60 lots of minus 12, minus 304, divided by A, which is 4. So we can conclude then C is equal to, well, here we've got 4 minus 60 lots of minus 12 minus 304 over 4, which is 105. We have found the values of A, B, and C. Question number 4. For part I, we're given A is a 2 by 2 matrix and B is a 2 by 3 matrix. Giving a reason for your answer, we have to explain whether it's possible to evaluate A, B, and then A plus B. Well, first of all, it is possible to calculate A, B, and that's because the number of columns in A is equal to the number of rows in B. And for the next part, to calculate A plus B, that's not possible because A and B have different dimensions. Now for the next part, we're given this matrix minus 5, 3, 1, A, 0, 0, B, A, B, multiplied by this matrix here, 0, 5, 0, 2, 12, minus 1, minus 1, minus 11, 3, and this is equal to lambda lots of the identity matrix. A, B, and lambda are constants, and we have to determine the value of lambda, A, and B. So we've got these matrices over here, and multiplying these together we get lambda lots of the identity, which is this matrix here. Now for us to determine the value of lambda, how could we get that? Well, if we focus on this top element here, we go across here, and then we go down here to find out that element. So we have 5 lots of lambda, rather 5, we'll just correct this actually. We go down here. So we've got 5 lots of 0 plus 3 lots of 2 plus 1 lots of minus 1, this here is equal to lambda. So what we can do from here is find out the value of lambda. 6 minus 1 is 5, and so therefore lambda is equal to 5. Now, to find out what B is and what A is, well, what we could do is work across here and then work down here. The result of this is this matrix over here, element over here. So we have B lots of 0 plus A lots of 2 plus B lots of minus 1 this is equal to 0. And so we have 2A minus B equals 0. What else can we do? Well, we could also go across here and then down here, and that will tell us this over here. So we have A lots of 5 and then we have 0 lots of 12 and then we have 0 lots of minus 11 . The result of this is equal to lambda. 5A is equal to lambda, and we know that lambda is 5, so we have 5A equals 5. A is equal to 1. And knowing that A equals 1, if we substitute back into here, we have 2 lots of 1 minus B equals 0, B equals 2. So we have found the values of A, B and lambda. And now for the next part we have to deduce the inverse matrix of this. Well, we'll replace A with 1 and B with 2. If we let A equal this matrix, of course we've replaced A with 1 and B with 2. We can use our calculator to find the inverse of A. So if we go to the matrix sub-menu, we've got 3 rows and 3 columns, and if we type in this matrix, we have minus 5, 3, 1, 1, 0, 0, 2, 1, 2. And if we click options, load up matrix A, we want to find the inverse of this. So the inverse of this matrix, well, you can see if we take out 1/5 as a factor, we've got 0, 1. So here we need 5. Here we've got 0. Here we've got 2/5. So 2 goes here. Here we've got 12/5. So 12 goes here. Minus 1 goes here. Minus 1 also goes here. Minus 11 goes here. and 3 goes here. So this is the inverse of that matrix. And now for the third part, we're given this matrix M, which is equal to 1, 1, 1, 0 sine theta, cos theta, 0 cos 2 theta, and sine 2 theta, where theta is in between 0 and pi. We have to determine the values of theta for which M is singular. So we've got this matrix M over here. Now, if we were to determine the values of theta for which M is singular, this would suggest then, if we write this down in a different colour, this would suggest that we want the determinant of M to equal 0. We have a singular matrix. So we need to calculate the determinant of M. So if we were to calculate the determinant of M, expanding along this column, well, if we cover up this row and this column and then take the determinant of what's left over, multiplying it by 1, we've got 1 lots of sine theta, sine 2 theta, minus cos theta, cos 2 theta. And then, if I move this down here, we've got minus 0 lots of 1 times by sine 2 theta minus 1 times by cos 2 theta, and then we have plus. If I move this down here, we've got 0 lots of 1 times by cos theta minus 1 times by sine theta. So having done all that, you can see the determinant of M is equal to sine theta, sine 2 theta minus cos theta, cos 2 theta. And if we go to the formula book, what would you notice? Well, under the regular A-level maths section, you will remember that cos A plus minus B is equal to cos A cos B minus plus sin A sin B. Now here we've got A plus, which means we'd have to have the, rather, if we compare this with what we have here, we can take out a minus 1, leaving us with cos theta, cos 2 theta minus sin theta, sin 2 theta, and then if we compare with what we have here, we've got a minus here, which means we should have the plus here. Now A is theta, B is 2 theta, which means we end up with minus cos of theta plus 2 theta. So we have minus cos 3 theta. And because we know that the determinant is equal to 0, we have minus cos 3 theta equals 0. cos 3 theta is equal to 0. Now, on our calculator, if we work out the inverse cosine of 0, we get pi over 2. So 3 theta is equal to pi over 2. And if we do 2 pi minus this, we get 3 pi over 2. And then if we add on 2 pi to a half pi, we get 5 pi over 2, from which we see theta is equal to pi over 6, 3 pi, rather we've got 3 pi over 2 divided by 3, so that's just pi over 2. And then here we've got 5 pi over 6. So these are our values of theta. Question number 5. For part I, we have to evaluate the improper integral of 2e to the minus 1/2 x with respect to x in between 1 and infinity. So, we begin by writing down the integral which we need to evaluate. We've got limits from 1 to infinity, and then we've got 2e to the power of minus x over 2 dx. And the way we approach this, well, you can see our upper limit is an infinity. So we need to take the limit as t tends towards infinity of the integral from 1 to t of 2e to the power of minus x over 2 with respect to x. So if we work this out, integrating 2e to the minus x over 2, we end up with minus 4e to the power of minus x over 2. So this result here needs to be evaluated from 1 to t, and then we need to take the limit of t as it tends towards infinity. So, if we work this out, well, we still have the limit as t tends towards infinity, and working this out, we have minus 4 e to the power of minus x over 2 minus 4e to the power of minus 1/2. And as t tends towards infinity, this tends towards 0. So we have 0, and then we have minus and a minus, which is a plus. And then we have 4e to the power of minus 1/2, which is quite simply 4e to the power of minus 1/2. And now, for the next part, the air temperature, theta degrees C, on a particular day in London is modelled by the equation theta equals 8 minus 5 sine of pi t over 12 minus cos of pi t over 6, where t is in between 0 and 24, and t is the number of hours after midnight. For part A, we have to use calculus to show that the mean air temperature on this day is 8 degrees C, according to the model. So we have our equation for theta, and bear in mind, theta is in between 0, rather t is in between 0 and 24. So for part A, we have the integral of theta between 0 and 24. And because we are finding the mean temperature, we need to multiply this by 1 over 24 minus 0. So if we continue to work all of this out, well, we still have the 1 over 24. And then integrating 8, we end up with 8t. Integrating minus 5 sine of pi t over 12. Well, don't forget, we need to divide by the differential of the bracket. Minus 5 divided by pi over 12, that's 60 over pi. And then integrating minus sine, we end up with positive cosine. So we add on 60 over pi, lots of the cosine of pi t over 12, and then integrating cos, we end up with sine. So we've got minus, and then 1 over pi over 6 is 6 over pi, and then we have sine of pi t over 6, and all of this needs to be evaluated between 0 and 24. So we have 1 over 24 lots of, well, if we retain these square brackets, for our upper limit, we have 8 lots of 24, then we add on 60 over pi, lots of the cosine of 24 pi over 12, minus 6 over pi, lots of the sine of 24 pi over 6. For our lower limit, we have 8 lots of 0 plus 60 over pi, lots of, well, here we'd have the cosine of 0, and then we subtract off 6 over pi, lots of the sine of 0. So this is what we need to evaluate. So for the upper limit, we have 1 over 24 times by, well, let's just leave this as it is. So we've got 1 over 24 lots of well, here we've got, for the upper limit, 8 lots of 24, and then we have here 12 pi, rather 24 pi over 12, which is 2 pi, so cos of 2 pi is 1, so we add on 60 over pi, lots of 1, and then we subtract off 6 over pi, lots of sine of 0, which is 0. So this is what we get for our upper limit, and for the lower limit, we have 0 for 8 lots of 0, And then the cosine of 0 is 60 over pi. So we add on 60 over pi lots of 1. And then we subtract off 6 over pi lots of 0. So this is what we need to evaluate. Well, let's cross off all the terms that equal 0. This and this equal 0. And then we have 60 over pi minus 60 over pi. So that's 0. And then we've got 1 over 24 lots of 8 lots of 24. Well, this and this cancel out, leaving us with a value of 8. And so therefore, the mean air temperature is 8 degrees C. And then for part B, given that the actual mean air temperature recorded on this day was higher than 8 degrees C, we have to explain how the model could be refined. Well, if it's higher than 8 degrees C, we've also got 8 here. We need to make this 8 higher. So we could increase the value of the constant 8. Now this 8 over here quite simply refers to this 8 here. So that's how we could refine our model. Question number 6. A tourist decides to do a bungee jump from a bridge over a river. One end of an elastic rope is attached to the bridge and the other end of the elastic rope is attached to the tourist. The tourist jumps off the bridge. At time t seconds after the tourist reaches their lowest point, their vertical displacement is x meters above a fixed point, 30 meters vertically above the river. When t is 0, x is equal to minus 20. The velocity of the tourist is 0 meters per second, and the acceleration of the tourist is 13.6 meters per second squared. In the subsequent motion, the elastic rope is assumed to remain taut so that the vertical displacement of the tourist can be modelled by the differential equation 5k lots of d squared x over dt squared plus 2k lots of dx over dt plus 17x equals 0, where t is greater or equal to 0, k is a positive constant, and we have to determine the value of k. Well, we know already x is equal to 20. We also know the velocity is 0 meters per second. Velocity, that's displacement differentiated with respect to time. And the acceleration is 13.6 meters per second squared. So that's what d squared x over dt squared is. We can substitute these values in to this differential equation to find the value of k. So for part A, if we substitute into the differential equation, we have 5k lots of 13.6. So this 13.6 is the acceleration plus 2k lots of 0. The velocity is 0 plus 17x, so we add on 17 lots of minus 20. This is all equal to 0. So we can find out what k is. 5 times 13.6 is 68. So we have 68k equals, well, 17 times by 20, that's 340. So 68k is 340. So therefore, k is equal to 5. And knowing the value of k, we can therefore conclude our differential equation. Well, we've got 5k, so that's 5 times by 5, which is 25. We've got 25 d squared x over dt squared plus 2k, so we add on 10 lots of dx over dt minus plus 17x. This is all equal to 0, and t is greater or equal to 0. And now for part B, we have to determine the particular solution to the differential equation. For part B, we would begin by forming the auxiliary equation. The coefficient of the second derivative becomes the coefficient of m squared. The coefficient of the first derivative becomes the coefficient of m. The coefficient of x becomes the constant term. So the auxiliary equation is 25m squared plus 10m plus 17 equals 0. And if we find out the solutions to the auxiliary equation, we've got 25m squared plus 10m plus 17. So we get m equals minus 0.2 plus minus 0.8i. And so knowing our auxiliary equation solutions, we can therefore conclude our general solution is equal to e to the minus 0.2t lots of a times by the cosine of 0.8t plus b times by the sine of 0.8t. We have complex roots for our solutions to the auxiliary equation, so our general solution is of this form here. Now we can substitute in these conditions. Now, because we've been given information about the velocity when t equals 0, it would make sense for us to differentiate x. So if we differentiate x, dx over dt using the product rule, well, we have u dash times by v which is a times the cosine of 0.8t plus b times by the sine of 0.8t, and then we add on u which is e to the power of minus 0.2t times by v dash which is minus 0.8 a sine of 0.8t plus 0.8 b times by the cosine of 0.8t. So now let's substitute in our conditions. We know when t is 0, x is minus 20. So t equals 0, x equals minus 20. We've got minus 20 equals e to the power of 0 multiplied by, well, here we've got a times by the cosine of 0, and then we add on b times by the sine of 0. So, recognizing that the cosine of 0 is 1 and the sine of 0 is 0, we have minus 20 equals a. This is our solution for a. And then we also know that when t is 0, the velocity is 0 meters per second, which means dx over dt is equal to 0. So we have 0 equals minus 0.2t to the power of 0 multiplied by a times by the cosine of 0 plus b times by the sine of 0 plus e to the power of 0 lots of minus 0.8 a times by the sine of 0 plus 0.8 b times by the cosine of 0. So we've got 0 equals minus 0.2 times by a, and then here we've got 0.8 times by b. Of course, cosine of 0 is 1, sine of 0 is 0. We know what a is, that's minus 20. So we've got 0 equals minus 0.2 times 20 plus 0.8b. We can therefore find out what b is. If we find out what b is, 20 times 0.2 divided by 0.8, that's 5. So we have b equals 5. Rather, b equals minus 5. So, knowing the values of a and b, our particular solution then, we'll call it x. PS, that's equal to e to the minus 0.2t multiplied by minus 20 times by the cosine of 0.8t minus 5 times by the sine of 0.8t. This is our particular solution to the differential equation. And now for part C, hence find, according to the model, the vertical height of the tourist above the river 15 seconds after they have reached their lowest point. Well, what else do we know? We know that we have x meters above a fixed point. Well, we are 30 meters above this fixed point. So the vertical height is equal to 30, and that comes from here. What we mentioned, that was given to us in the question, plus, well, we know that t is equal to 15. So we have e to the minus 0.2 times 15 multiplied by minus 20 times by the cosine of 0.8 times 15 minus 5 times by the sine of 0.8 times by 15. So if we work out the vertical height, we have 30 plus e to the power of minus 0.2 times by this, multiplied by minus 20 times by the cosine of this, minus 5 times by the sine of this. It turns out rather, here we have 0.8 times 15, and here we have 15, and here we also have 15. So we get 29.29, etc. So we have 29.3 meters given to 3 significant figures. And now for part D, we have to give a limitation of the model. Well, it's unlikely that the rope will remain taut. That's one limitation. Question number 7. The plane pi has equation r equals 332 plus lambda lots of minus 121 plus mu lots of 201. Lambda and mu are scalar parameters. We have to show that the vector 2i plus 3j minus 4k is perpendicular to pi. Well, if we take the dot product between this vector and these direction vectors and get 0, we can then conclude that this vector is perpendicular to pi. So, for part A, we have minus 121. So we've got minus I. So we've got minus I plus 2j plus k. If we take the dot product with this and 2i plus 3j minus 4k minus 1 times by 2, well, let's just write that down. We've got minus 1 times by 2, 2 times by 3, and then we have 1 times by minus 4. So we've got minus 2 plus 6 minus 4, which is 0. And then we also have the other direction vector, 201. So we've got 2i plus 0j plus k dot with 2i plus 3j minus 4k, 2 times by 2, 0 times by 3, 1 times by minus 4. It turns out here we get 0. So what can we say from this? Well, we've got this vector which is perpendicular to this direction vector and this direction vector, and so as 2i plus 3j minus 4k is perpendicular to both direction vectors of pi, the direction vectors being this and this, then this vector must be perpendicular to pi. So then the normal vector is equal to 2i plus 3j minus 4k. Now for part B, hence find a Cartesian equation of pi. Well, if we go to the formula book, we have n1x plus n2y plus n3z plus d equals 0, where d is equal to minus a dot with n, where n is this normal vector and a is a position vector on the plane. Now, if I take the d over to the right hand side, then we'd have positive a dot n. So we need to find out what d is. D is equal to a, which is 3i plus 3j plus 2k, and then we will dot this with this vector here. So we've got 3 times by 2 plus 3 times by 3 plus 2 times minus 4, 6 plus 9 minus 8 is 7. And so what we can conclude then is the equation of the plane. We have r dot with this vector here this is equal to 7. So in other words, for the equation of pi, we have 2x plus 3y minus 4z equals 7 in Cartesian form. Now for part C, the line L has equation 4 minus 5, 2 plus t lots of 1, 6 minus 3, and t is a scalar parameter, and the point A lies on L, and given that the shortest distance between A and pi is 2 times the square root of 29, we have to determine the possible coordinates of A. Well, if we write A as coordinates with t lying, with A lying on L, for part D, we begin by letting A with coordinates 4 plus t minus 5 plus 6t 2 minus 3t lie on L. So this coordinate here lies on L. And if we go to the formula book, this is how we find the perpendicular distance from a point to a plane. Now we know all these values of n1, n2 and n3. We know the value of d, and we know alpha, beta and gamma. That's a point, and we're finding the perpendicular distance from this point. Substituting everything in, we have the mod of, well, we've got 2. Well, perhaps if we just change the colour of this, we've got 2. And then we've got 3. And then we've got minus 4. So we've got here 2 lots of x, which is 4 plus t. And then we've got plus 3 lots of minus 5 plus 6t. And then we've got minus 4 lots of 2 minus 3t. And then we've got minus 7, because remember, if we take it over to the other side, we'd have minus. So we've got minus 7. Remember, all this is modded. And then we divide this by, well, we've got 2 squared plus 3 squared plus minus 4 squared, and then this is square rooted. And the result, we have 2 times by root 29. So let's tidy all of this up as much as possible. We have the mod of, well, 2 times by 4 is 8. 2 times t is 2t. 3 times minus 5 is minus 15. 3 times 6 is 18, and then we times that by t. Minus 4 times 2 is minus 8. And then minus 4 times minus 3t, that's positive 12t. Then we've got the minus 7, and all this is modded. This is equal to, well, 2 squared plus 3 squared plus 4 squared square rooted is root 29, and if I times this by 2 root 29, I get 58. So if I tidy this up even further, we've got 32t minus 22 modded equals 58. Replacing the mod signs with plus minus, we've got plus minus 32t minus 22. This is equal to 58. So if I take the positive, we've got 32t minus 22 equals 58. And if I solve for t, 58 plus 22 divided by 32, that's 5/2. So we get t equals 5/2. And if I take the negative, we've got 22 minus 32t equals 58. So 58 take away 22 divided by minus 32. That's minus 9/8. So we have t equals 5/2 and t equals minus 9/8. And knowing the value of t, we can substitute these into here. So perhaps if we use different colours. So here we get t equals 5/2. And here we get t equals minus 9/8. We can find out the different values of a. So from here, a would equal, well, we have 4 plus 5/2. That's the coordinate. So we said a was this here. Then we've got minus 5 plus 60. So then we have minus 5 plus 6 lots of 5/2. And then we have 2 minus 3t. So we've got 2 minus 3 lots of 5/2. So therefore, one possible coordinate of a, we have 23/8 minus 47/4 and 43/8. That's one possible coordinate. Or if we substitute in minus 9/8, we have 4 plus minus 9/8 minus 5 plus 6 lots of minus 9/8. Rather, we get this result for the coordinate when t equals 5/2. And then here, if we continue on, we get 2 minus 3 times by minus 9/8. So from this we can conclude A has coordinates 23/8, 10, rather not 10, minus 47/4, and 43/8. So we've got two possible coordinates for A. Question number 8. Two different colours of paint are being mixed together in a container. The paint is stirred continuously so that each colour is instantly dispersed evenly throughout the container. Initially, the container holds a mixture of 10 litres of red paint and 20 litres of blue paint. The colour of paint mixture is now altered by adding red paint to the container at a rate of 2 litres per second and adding blue paint to the container at a rate of 1 litre per second and pumping fully mixed paint from the container at a rate of 3 litres per second. We let our litres be the amount of red paint in the container at time t seconds after the colour of the paint mixture starts to be altered. For part A, we have to show that the amount of red paint in the container can be modelled by the differential equation dr over dt equals 2 minus r over alpha, where alpha is a positive constant to be determined. How much paint do we have in total? Well, we've got 10 litres of red, 20 litres of blue, and so for part A, the volume of paint, we've got 10 litres of red plus 20 litres of blue, which is 30 litres. So dr over dt would represent the rate of red paint in the container. So what's the rate of red paint going in? Well, that's 2 litres per second. So the rate of red paint in, we have 2 litres per second, and the rate of red paint out we can determine with the information given here. So the rate of red paint out, well, we know already that we pump from the container at a rate of 3 litres per second. And how much red paint do we have? Well, out of 30 litres, that's how much we've got in total. R of those litres is red. So here we have R over 10 litres per second. So this is the rate of red out. And so therefore, dr over dt, we have in, which is 2, out, which is r over 10. So the rate then is 2 minus r over 10 litres per second. Alpha is therefore equal to 10. And now for part B, by solving the differential equation, we have to determine how long it will take for the mixture of paint in the container to consist of equal amounts of red paint and blue paint according to the model. Give your answer to the nearest second. Well, if we take a look at this differential equation, we can rearrange to write it in an integrable form. So we've got dr over dt plus 1 over 10 r equals 2. And we can write down the integrating factor. The integrating factor is equal to e to the power of the integral of 1 over 10t dt. So we have the integrating factor equaling e to the power of 1/10 t, which I'm going to write as t over 10. So the general solution, we've got r multiplied by e to the power of t over 10. This is equal to the integral of 2 lots of the integrating factor, and then we integrate this with respect to t. So if we integrate this, our solution, we've got r e to the power of t over 10 equals 20e to the power of t over 10 plus c. Now we've been given conditions. We know initially we've got 10 litres of red paint. So when t equals 0, r is equal to 10. So we've got 10 times by e to the power of 0 equals 20 e to the power of 0 plus c. So therefore c is equal to minus 10. And knowing that c is equal to minus 10, the particular solution, we have re to the power of t over 10 equals 20 e to the power of t over 10 minus 10. This is the particular solution to the differential equation. Now what we have to do is find out the time it takes for us to have equal amounts of red paint and blue paint. So that would imply R equals 15. So let's just write down the reason for this. R is 15, and that's because we've got equal amounts of blue and red, and we've got 30 litres in total. So that's how much paint we have in total, and if we divide that by 2, we get 15 litres. So R is 15. So with R equaling 15, we have 15 e to the power of t over 10 equals 20 e to the power of t over 10 minus 10. So we have 5e to the power of t over 10 equals 20, rather equals 10. E to the power of t over 10 equals 2. So 1 over 10 times by t is equal to the natural log of 2. So t is equal to 10 times by the natural log of 2, which if I work this out, we get 6.931, etc. So therefore we have t equals 7 seconds to the nearest second. And now for part C, it actually takes 9 seconds for the mixture of paint in the container to consist of equal amounts of red paint and blue paint. We have to use this information to evaluate the model, giving a reason for your answer. So the model predicts 7 seconds, that's what we found here, but it actually takes 9 seconds, so we're 2 seconds out, so we don't have a good model. Question number 9. For part A, we have to use a hyperbolic substitution in calculus to show that the integral of x squared over the square root of x squared minus 1 with respect to x is equal to 1/2 lots of x lots of the square root of x squared minus 1 plus the inverse hyperbolic cosine of x plus some constant k. Now, if we go to the formula book, we've been given an identity over here. We know already that hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. Now, if we pay attention to what we are integrating, well, here you can see we've got a x squared minus 1. We want something of that form. Now, if I rearrange for hyperbolic sine squared, hyperbolic sine squared is equal to hyperbolic cosine squared minus 1. This matches the form we have over here. And whilst we're at it, hyperbolic sine then is equal to hyperbolic cosine squared minus 1 square rooted. So if we let x equal hyperbolic cosine of u then is equal to the inverse hyperbolic cosine of x, just in case we need it later on. And dx over du this is equal to hyperbolic sine u, and so dx is equal to hyperbolic sine u du. So what's our integral? Well, our integral is x squared over the square root of x squared minus 1 dx. And if we replace the variable x with hyperbolic cosine of u, this integral would become the integral, well, we have x squared, so that's hyperbolic cosine squared of u, over hyperbolic cosine squared of u minus 1 square rooted, and then dx we've said is hyperbolic sine of u du. So let's simplify all of this. We have the integral of hyperbolic cosine squared of u over, well, cosine squared u, hyperbolic cosine squared u minus 1, that's hyperbolic sine squared, and then square rooting that we get hyperbolic sine. And then we've got hyperbolic sine u du. This and this cancel out for us happily. So we've got the integral of hyperbolic cosine squared of u du. Now, do we know what hyperbolic cosine u squared is? Well, we can use the fact that hyperbolic cosine of 2u is the same as 2 lots of hyperbolic cosine squared of u minus 1. And so hyperbolic cosine squared u is equivalent to 1/2 lots of hyperbolic cosine 2u plus 1. And so this integral here is, well, if I take the 1/2 out, we've got 1/2 lots of the integral of hyperbolic cosine of 2u plus 1 du. And so if I integrate, we have 1/2, and then we're multiplying this by hyperbolic cosine of 2u, that's 1/2 times by hyperbolic sine of 2u, and then we add on the integral of 1, which is u. and then we add on some constant k. Now, hyperbolic sine of 2u, if we go to the formula book, we can use this result here. Hyperbolic sine of 2x is equal to 2 times by hyperbolic sine x, hyperbolic cosine x. And so we have here 1/2, lots of the 1/2 times by 2 hyperbolic sine u, hyperbolic cosine u, plus u, and then we add on some value k. Now, hyperbolic sine u, we can use the fact that that's square root of hyperbolic cosine u minus 1. And then we've got the 2 times by 1/2, which is just 1. So we have here 1/2 multiplied by here we've got hyperbolic sine u, which is hyperbolic cosine u squared minus 1 square rooted multiplied by hyperbolic cosine u plus u, and then we add on k. Now, if we rewrite these in terms of x, we know that x is equal to hyperbolic cosine u, and so we end up with 1/2 multiplied by, well, here we have x, and here we have x squared minus 1 square rooted and then u, that's equal to the inverse hyperbolic cosine of x. And then we add on some constant k. So this is exactly the result which we wanted to show. Now for part B, figure 1 shows a sketch of part of the curve C with equation y equals 4/15 x times by the inverse hyperbolic cosine of x, where x is greater or equal to 1. That's what we see here. The finite region R, shown shaded in figure 1, is bounded by the curve C, the x-axis, and the line with equation x equals 3. We have to use algebraic integration and the result from part A to show that the exact area of R is given by 1/15 times by 17 lots of the natural log of 3 plus 2 root 2 minus 6 root 2. Well, the area of R, we can integrate between 1 and 3, this curve here. So, for part B, the area of R is given by the integral from 1 to 3 of 4/15 times by x times by the inverse hyperbolic cosine of x dx. That's how we find the area. Now what we'll do over here is we'll just consider the integral without the limits. So if we consider the following integral, well, let's take out the 4/15. Then we've got the integral of x times by inverse hyperbolic cosine of x dx. U is equal to inverse hyperbolic cosine of x. U dash, well, if we go to the formula book, if I differentiate hyperbolic cosine, inverse hyperbolic cosine, I end up with 1 over square root of x squared minus 1. So u dash is equal to 1 over x squared minus 1 square rooted. V is equal, well, v dash rather is equal to x, and v, that's equal to 1/2 x squared. So when we come to use integration by parts, you can see then 4 over 15 lots of the integral of x times by inverse hyperbolic cosine x with respect to x. This is equal to, well, we've still got the 4 over 15. And then if we open up a big bracket, we've got v times by u. So we've got 1/2 x squared times by the inverse hyperbolic cosine of x, and then we subtract off, well, let's just use larger brackets here. So we've got 4 over 15 lots of 1 over 2, and then here we've also got 4 over 15 lots of this. Then we subtract off vu dash, so that's 1/2 lots of the integral. Well, here we've got x squared over x squared minus 1 square rooted dx. And we add on some constant of integration. We'll call it a for a moment. Now, the justification for us to have u and v dash in this order, you can see it worked out quite nicely, that when we substitute it back into the integration by parts formula, we ended up with an integral of x squared over square root of x squared minus 1, which is what we worked out in part A. And that was a suggestion for us. We could use our result from part A. So if we use our result from part A, well, we have over here 4 over 15 lots of, well, we've got 1/2 x squared times by inverse hyperbolic cosine of x minus 1/2. And then here, be careful, we worked out this result here previously. We worked out this result to be this over here. So we need to be careful with our brackets. Perhaps if I copy and paste, well, we'll leave that alone. We've got 1/2 lots of 1/2. Well, let's just use curly brackets here actually. We've got 1/2 lots of 1/2 lots of x lots of x squared minus 1 multiplied by the cosine of x. And then just be careful with your brackets. And then we close this big bracket here. So hopefully that all makes sense so far. And then we've got this constant of integration a. Now, what I'm going to do is multiply the 4 over 15 into this entire bracket. So if we do that, we have 4 over 15 times by a half, which is 2 over 15. And then we've got x squared times by the inverse hyperbolic cosine of x. And then here we've got a half times by a half times by 4 over 15. So that's minus 1 over 15 times by x squared minus 1 square rooted. And then here we've got half times by this times by another half, and don't forget we've got the minus, so we subtract then 1 over 15 times by the inverse hyperbolic cosine of x, and then we add on some constant of integration as we see here. Now our limits are 1 and 3. Now before we do anything else, let's just make clear where this came from. That is the result of integrating this over here. So if we continue to work all of this out, we can therefore conclude that the integral from 1 to 3 of 4 over 15 x times by inverse hyperbolic cosine of x dx is equal to, well, let's open up our big bracket. We have 2 over 15 times by x squared times by the inverse hyperbolic cosine of x minus 1 over 15 times by x times x squared minus 1 square rooted minus 1 over 15 times by the inverse hyperbolic cosine of x, and then we evaluate this between 1 and 3. Now let's substitute in for our limits. For our upper limit, we've got 2 over 15 times by 3 squared times by the inverse hyperbolic cosine of 3 minus 1 over 15 times by 3 times by 3 squared minus 1 square rooted minus 1 over 15 times by the inverse hyperbolic cosine of 3. So this is what we get for our upper limit. And for our lower limit, we've got 2 over 15 times by 1 squared times by the hyperbolic cosine, the inverse hyperbolic cosine of 1, minus 1 over 15 times by 1 squared minus 1 square rooted minus 1 over 15 times by the inverse hyperbolic cosine of 1. That's our lower limit. So the lower limit is just equal to 0 because the inverse hyperbolic cosine of 1 is just 0. So this gives 0, this gives 0, and this also gives 0. So we've got 9 times by 2 over 15 minus, which is 18 over 15, minus 1 over 15, so that's 17 over 15, and then we've got the inverse hyperbolic cosine of 3, and then we've got here 3 times by root 8 divided by 15, so that's minus 2 root 2 over 5. And if we factorize out a 1 over 15, we've got 17 times by the inverse hyperbolic cosine of 3 minus 6 root 2 and let's work out this result. We can go to the formula book under the hyperbolic section. Here is how we work out the inverse hyperbolic cosine of x. It's the natural log of x plus square root of x squared minus 1. So we've got 1 over 15 times by 17 lots of the natural log of 3 plus 3 squared minus 1 square rooted, and then we've got minus 6 root 2. So this over here simplifies to 3 plus 2 root 2. So we've got 1 over 15 multiplied by 17 times by the natural log of 3 plus 2 root 2 minus 6 root 2. And then let's close this big bracket. So this here is the area of our